So Covey Concrete is a concrete subcontractor that we've done a lot of work with, probably well over 100 parking structures with. And this is one of the ones that we're doing out in Cyprus, or we did. This was 2002. But I just love the drone stuff that they're able to do now. And more than just being fun, we're actually able to document pretty darn closely where the post tensioning is and where the rebar is. And if you have to come back later and you really want to zoom in and try to figure out if you can core something or what happened when something goes wrong, there's as good evidence. So this is actually a flat plate structure. In effect, effectively a flat plate structure is just building beams inside a constant thickness slab. So if I stop this, these are beams, and we run one-way slabs going this way. So it's not entirely different philosophically than a one-way slab and beam system. It's just that it looks much nicer without having the beam drop down below the slab, and ownership likes it. Everybody likes it. The architects like it. The downside is it can only go somewhere in the 30s foot range, somewhere in the 32, 34. Whereas the beams, dropping them down, will easily go into the mid 60s range or farther. So, but this is really kind of our bread and butter. This type of system is what Brian and I do a lot of, and we do a lot of it with Covey. We also do it with Silverline. We do it with a lot of Guy Yoakum. So I don't want to single anybody out and forget anybody else, but we've certainly done plenty of these garages. This is waiting for it's called a wrap type style garage. It's waiting for apartments to be built all around it. So the reason it's called a wrap is the apartments will wrap the parking structure and we'll be in the middle of it all, and typically you won't even be able to see our parking structure anymore. So anyway, thought you might like to see that. We're moving on to the project. So the culmination of everything you've done in the homework assignments up till now is going to happen again in the project. And it's fun. So really you shouldn't be seeing anything you absolutely haven't seen, except we get a little more refined in some of it. What I'm showing you right here, as I've said, not necessarily your project. It might be this year, but I have decided, for a variety of reasons, to really take my foot off the gas on this project. I'm getting older. It's probably the main reason. I've got to grade these, and Brian and I grade these, and it's grueling. The UCLA class 2 years ago was 48 students, so trying to grade, and the Cal Poly class is in the mid-20s. So, I'm up over. 2 years ago, I had to grade 70 of these things between the two of us, and when I make the project hard, it's hard on me too. So it's not just on you. We've now expanded. We're teaching this through SK Ghosh, so you may be watching this through the SK Ghosh program. And you're practicing professionals, and you don't need to do the design at every single joint and design the rebar at the grid A, left side of grid B, right side of grid B, and grid C, and do as much as I had the students do before. So it's a new trail we're blazing. I am turning these into homework assignments as opposed to just one big project that I drop on you in the 6th week. So I think this is going to work out better for all of us. But I want to give you the general idea. I'm still going through the book example. So I will go through the book example the way I've always done it, and I will point out what I'm going to be asking you to do in your project / homework assignments. I've broken this project up into 3 homework assignments. That's the idea, at least right now. And they're going to be heavily weighted. So these 3 homework assignments will be worth much more than the previous homework assignments. So, but the idea I want to point out is I'm going to give you a floor. It's going to be a 2-span beam. There'll be some type of loading on one side and some type of loading on the other side. I will have you design one 2-span beam. But really, we're going to be doing this by hand all the way through. Now, like I said, the only difference is I'm going to take my foot off the gas and not have you literally do every significant maxima point on this. Not necessarily both spans designed flexurally, bottom span, negative moments at all supports, etc., etc. So, and things that were mandatory before, I'm going to make optional for extra credit. So that's the idea. We'll see how it goes. Cal Poly's going to a semester system, so dropping a very significant project right in the middle of the semester doesn't seem like such a great idea there either. So, and like I said, the UCLA class was really large. The Cal Poly class going to semesters, and these SK Ghosh and Associates class is design professional. So nobody, I think, really wants to be doing a long, grueling project. But you're still going to get all the major points out of it. Forget all this stuff up here right now. What I want you to focus on is that we have a concrete system that has columns, that has beams, and because it has columns and beams, it has rigid zones. And we're going to talk about that kind of right off the bat. But because of those rigid zones, every professional software program is going to create a stiffness matrix that is not a stiffness factor of 4 EI over L and a carryover factor of 0.5 and fixed end moments of WL squared over 12. They're going to be something else, and that's how the stiffness matrix is created. You probably did at some point in mechanics of materials or your structural analysis class the proof of those, or you should have, I hope. But you didn't do the proof of these. So something with a rigid zone where EI is not constant from the center line of the joint to the opposite center line of the joint. So that's our first order of business. But I want you to understand I'm giving you these values. Going through and proving them, my current train of thought is that I am going to make it an extra credit. You're not going to have to do this. For those of you who are aggressive and like to do everything, you really want this thing to be done by hand beginning to end, then you might, sorry, my nose itches, you might want to go through and prove one of these beams and one of these columns maybe. But I'm going to kind of leave that up to you. So again, I'm going to show you how these were generated, but you're not required to do it. Okay, so here's my design example. I have a 62-foot beam and a 44-foot beam. This is just parking structure loading. I've made my example much easier than I'm probably giving you. So that's just the way I am. It's the kind of guy I am. I want you to see that how this works. This is how we do it in practice. These T-beams don't stop at the edge of the T-beam. They're really just the slab. We create a T-beam out of this using the web plus 8 times T on each side. T being the thickness of the slab. So we create our own T-beam, and then we'll use that as the section properties. And I want you to do that. You will be doing that. I will give you the column size. I will give you the column dimensions. I do actually have you currently calculating the section properties. So you're going to create the T-beam, create the section properties. And within, I will give you the PT data output, and you can verify basically everything with that to see if you've done it right. The real beauty of this design project is I give you the output from PT data, and that's what we're trying to match. That's the game here. The real beauty is you don't have to come to me and ask me if you've done it right. You just are checking yourself. So I love that part. Okay, so I give you the material properties. This is what I had students do in the past. Because this is what we do in practice. We calculate what a 5-inch slab weighs in pounds per square foot. This is practice. Those of you who are practicing engineers will know this already. We'll convert the beams that we have to pounds per square foot also. In fact, we try to convert everything to pounds per square foot. That's just the way a load criteria sheet works. We'll have miscellaneous load. If we have it, we'll have ceiling load, we'll have flooring load, we'll have whatever other load we have in a particular building, and it will be in terms of pounds per square foot. And we work off tributary areas to get to line loads. And that's the idea, is this would have some tributary area here to this beam. On one side, the tributary area is 10 feet. On the other side, it was 20 feet. But we multiply the pounds per square foot times the tributary area, get a line load on the beam. That's all fine. My frustration in the past has been that some students, and I'm talking to you Cal Poly students, really don't use enough significant digits in your calculations. That's a Cal Poly thing. I went to Cal Poly. I know what you mean. We used to have a phrase, close enough for government work. We weren't concerned about being too accurate. I think we understood that we were engineers, not scientists, not mathematicians. But in this case, we're trying to match a computer output. We're trying to see how close we can get. So we need to have significant digits. And I have requested in the past that we use 4 significant digits. Now, UCLA, on the other hand, students use about 9 significant digits. So I've got both ends of the spectrum, and in my opinion, the best answer is somewhere in between those two. But I think I've decided that I'm just going to give you the concrete load, the total dead load, and the total live load in kips per foot. So I'll give it to you, and I want you to use that number. So trying to eliminate that variation between being excessively accurate and not accurate enough. Because at some point, if you're just not accurate enough in your calculations and you're trying to verify your numbers with a computer output, you're going to be off. And you're going to get off so much that you don't know if you have a mistake or you've just rounded too much. And then I won't know either, and it gets to be a mess. So I think my general idea right now is that I will be giving you these numbers. You will factor them when you need to. Some of our calculations are at service level, as you remember. Some of them are at factored level. That's what we do. I'll also likely ask you, and my idea behind this is I want you to be able to start at some design, guess at some design, have a reasonable approximation of what a design should be, instead of just letting a computer figure it out for you. And this is what I'm doing here. The idea is to get a starting point. And if I didn't, now I'm giving you, don't get confused, I'm going to give you the force and profile, because I'm going to have, I don't know if I'm going to have 50 or 60 or 70 students when I'm teaching in the spring, but I can't have everybody doing their own thing. We're all going to do the same thing, at least with the post-tensioning force and drape. So I will give that to you, but I want to know that after taking my class, you could come up with an estimate of what it should be and see kind of how I got there just by doing some rough hand calculations. So in this particular case, not necessarily the one I'm giving you, but in this particular case, I just said balance approximately 70% of the concrete weight and provide a minimum of 250 psi in the section. A lot of times that's what your boss will just say. Just start with, this is back in the olden days before the computer software wasn't necessarily as advanced. We'd actually estimate and start with something, but we figured it out. So figure out what the concrete weight is, balance about 70% of it, figure out what force that relates to with a full drape, and then verify that you had some amount of pre-compression. 250 was an office standard that we used at Engelkirk's office. It's a good, I still use that now. So that just happens to be a value that we just don't feel we want to go less than. We just know after doing hundreds of these that will give a good design, should give a good design. So what I'm doing here, and I may be asking you to do it too on the project, maybe not with 70, but with a different amount of load balancing, is just show that the force in the profile that I gave you does balance this, or you could have come up with it something close on your own. So in this case, if the concrete dead load, which I gave you on the previous page, is 1.609 kips per foot, we want to balance 70% of that. That's 1.126. And we rewrite our equivalent load equation, 8FA over L squared, that we've gotten pretty comfortable with at this point in terms of the actual force. And we know that in the longest bay, we want a full drape. So we want the most drape we can get. We're going to go up to 4 inches from the top on the right. We're going to be at the center of gravity of the section on the left. And we're going to be at 4 inches from the bottom. That's about what you can do in post-tension concrete. It's a grouping of tendons. You got to get it inside the stirrups. There's a variety of reasons that 4 inches tends to be the smallest number we can use. So with that, we calculate an A value and decide that we need a force of about 267 kips to do this. Quickly, we look at what 250 psi is over this beam section of 940 square inches is. We need 235. Right now, we're estimating that we're going to use 267. That satisfies the 250 psi. So far, so good. Take 267 kips divided by 26.62 kips per tendon and get approximately 10 tendons. And that turns out what I'm going to use to be what I'm going to use in this design example. So again, if I was your boss or your boss told you balance about 70% of the dead weight of the concrete weight and provide 250 ksi, you, without me telling you or without a computer telling you, should be able to estimate that 10 tendons fully draped ought to do this. And if the computer program's giving you something wacky way away from that, that'll be a sign that something's not right. So then we go to the next span. So I've built in a short span in this particular case. So the 10 strands now have been established. So that 266.2 force is established. So what's left to figure out is what drape would we want to use. It's a shorter bay. We don't want to fully drape the shorter bay. This is the non-critical bay. So again, if we want to balance 70% of the load, we'll now rewrite the equation. Since F is now a given in this, we'll rewrite it in terms of A. The 8FA over L squared. We'll just keep reorganizing it for what we want to solve for. And in this case, A is 12.3 inches. So that's what I calculate to balance 70% of the weight in this span. So actually from the bottom, that works out to be 16 inches. So a good starting point, not necessarily guaranteed to work, but a good starting point. That's what design is. Design is taking a good educated guess at a starting point and then analyzing it to see if it was a good guess or how good a guess. If it wasn't that great of a guess, we adjust. But that's what design is. Okay, so I said in the homework, I probably will ask you to do something like that. Just show me that you don't need a computer to start. You don't need anybody but some basic direction of balance load and pre-compression to get going on a beam design. And a slab design too, by the way. But okay, so that was proving that we're in the ballpark, got a starting location. I've actually given you the force and profile. So now what I want you to do is not use what you estimated. Just scrap that. That was answering one of the homework assignments questions. Now you're actually going to calculate exactly what I gave you. So you'll calculate the equivalent load in span 1. You know how to do it. And the equivalent load in span 2. And that's what you're going to use in the project, is what I've actually given you. So not what you estimated. That was one question. Different part of this is that you're going to go forward with what was actually given. So that's confusing for some students and totally makes sense for other students. It's that way every year. Okay, so we need a moment distribution. We need to know a stiffness factor and a carryover factor, a fixed end moment factor. And like I said, those were 4EI over L, WL squared over 12, and a 0.5 carryover for most of your life as a student. It's not that case anymore. With concrete, we have rigid zones. And if we really want to match the software that we're using, and we want to match PT data, which we do, we're going to have to account for that. So it's no longer going to be those numbers anymore. So I'm going to show you how I came up with the fixed end moment, carryover factor, and beam stiffness K factor. Now, whether or not you decide you want to do this is up to you. I don't think this is all that difficult. Students have actually seemed to enjoy this. I always let the students write some software if you want to do this. This isn't something you have to do by hand. It's pretty easy, I think, to set up an Excel spreadsheet and use the solver. And I'll show you what you're solving for in a minute. But I'm taking the 62-foot beam, and I'm going to try, I am going to show you how I calculated the factors that are given to you in the project. Now remember our old moment area and curvature diagrams. These are the rigid zones. This is the center line. This is the center line. Column was 2 feet. So the rigid zone on one side of the center line is 1 foot. Both sides. Okay, so stiffness is considered infinite in that intersection between column and beam. So when we look at, I start, this is the way I do it. I put a 1 foot kip moment at one end, right there. That is going to translate to some moment that we don't know right now at the far end center line. That will end up establishing what the carryover factor is, but I don't want to ruin the fun for you just yet. A curvature diagram is taking that moment diagram and dividing by EI. So EI is infinite here, so there's nothing here. These values are now 0. That's the infinite stiffness part. Okay, so we set up, and what I'm asking you to do is, if you have a value of 1 here, you're going to have a value of something here depending on what this inflection point is. So set up your spreadsheet, make this the variable, and for any given value of x, that will establish just geometrically using similar triangles and what that value is, what this value at the face of the column is, and what this value is at the center line. So just in terms of inflection point x, you can establish those relationships. Now, why do we do that? Well, I will back up. The deflection at this point is 0. The deflection at this point is 0. The initial rotation at this side is also 0. So we're going to start and do our calculations from this side and establish what the deflection is at this side. So the way that is done, and I know that deflection is going to be 0 at this side, but the equation that I set up is that this area under the moment divided by EI, which is the curvature, the sum of the area under the curvature is rotation. So area under this curvature diagram establishes a rotation due to that curvature. And we locate it at the centroid of that triangle. So that's what we're calling L2. L2 from the point that we're calculating the deflection, which will be 0, is this rotation times L2. That's the contribution from this side. The contribution from this side is the area under the curvature diagram, which again is a rotation. Area under curvature equals rotation. So we add up all that area. That's how much rotation happened here. The centroid of that is at the geometric centroid of that triangle, and that's what we're dimensioning as L1. Now the rotation here times L2 minus the rotation here times L1 must be 0, because that's the deflection equation. Rotation times distance minus rotation times distance. Those must be equal to each other and opposite if that deflection is 0. Hopefully you've seen this before and this isn't brand new. So set up an equation for the deflection at A. A1 over EI times L1, that's what we just said, minus, I guess I get the A1 positive, so minus A2 over EI times L2. That must be 0 because the deflection at A is 0. Now, I've set up all these relationships. I've set this equal to 1. I iterated this and found that the value of x that solves this equation such that this area times that distance, or this area times that distance minus this area times that distance is equal to 0. So that number was 40.68 feet. You're going to do that for your beam. Good enough. Once I know that, I really know everything else. These are just triangles. So if I know this distance, I can now calculate that this is 0.9754, this is 0.4996, and at the center line, this is 0.524. Okay, that's really the difficulty in the entire thing. That's just about it. So out of this, we need a carryover factor and we need a beam stiffness factor. Let's start with the beam stiffness factor. How is this going to tell us what the beam stiffness factor is? Okay. The moment at A divided by the rotation at A for a unit value of the moment is this. Remember, the total rotation is this minus this. We put on a 1 foot kip moment. So moment divided by rotation is what we're looking at for stiffness. So that's a relationship. The relationship is usually written differently though. It's some K factor multiplied by EI divided by L per 1 radian. So it's a radian of rotation. What I had done is started with 1 foot kip of applied moment. To get into this form, we're going to need to convert that basically to 1 unit radian of rotation. But remember, these two are equal. This ratio is equal. It has to be. So I will set them equal to each other, and so will you. You'll notice that the EIs are going to cancel out. And what we're trying to do is establish a relationship for that K factor. So when I just solve for the K factor, I get the length of the beam, the 1 foot kip moment, and the EIs have canceled and everything, and I really have just area 1 minus area 2. So I can go calculate what area 1 is and what area 2 is. Once I established what that inflection point was, I've done that. I take the difference of A1 minus A2, and the stiffness factor is the length of the beam times 1 foot-kip of moment divided by A1 minus A2. And I calculate that the actual stiffness factor is not 4. It would be 4 if there was no infinite rigidity at either end of this beam, but because there is, it's now 4.343 EI over L. That's what the stiffness factor is, and that's actually what the computer programs are going to use. And that, we're really matching exactly what the computer program's doing, because we're going to establish a moment distribution that's based on exactly the same assumptions. So that was kind of the hard one. The carryover factor is actually very easy because it comes right out of, if this is 1 and the moment at the other center line is 0.524, the carryover factor is 0.524. So that's it. We now have the stiffness factor and we have the carryover factor. All that's left is to figure out what the fixed end moment factor is. Typically WL squared over 12 is everything we've been using. Not the case this time, and I have my own just very simplified way of doing this. To me, this makes sense. Remember, the deflected shape of this is going to be completely flat, then it's going to deflect, then it's going to come back and be completely flat. So completely flat, kind of come back up like this, and completely flat. So at these points, there has been 0 rotation. So here, it's the same thing as looking at the fixed end moment if the beam were just that long. So using this length, and I'm just cheating, I know that that's WL squared over 12 because I've been doing this my whole life. So the fixed end moment when EI is constant, and EI is constant for this entire length, is WL squared over 12 here. I also know that a shear diagram, this must be WL over 2 at the center line, and this must be WL over 2 at the center line, because I just have a constant uniform load. So that tells me what the increase in moment between this point and this point must be. It's the area under the shear diagram. Simple stuff. We've all known that for years. So if I can calculate what WL squared over 12 is based on this L, WL prime squared over 12, and I add this area here, then I know at the center line what the fixed end moment is. And from that, I will establish what the constant is. So at the face of the column, WL prime squared over 12 is 300 foot-kips. That's what it is right here. To get the moment at this point, I'm just adding the area under the shear diagram. 31 kips plus 30 kips divided by 2 times this 1 foot distance tells me that the center line moment must be 330.5 foot-kips. Good enough. We know in general terms that the fixed end moment is WL squared over something, typically 12, but not 12 here. And we'll set that equal to what we know it to be at the center line, the 330.5, and just solve for the new fixed end moment factor. And in this case, 11.63. So WL squared over 11.63 is what the stiffness matrix in the computer program is going to put in for fixed end moments. And we're going to use that same thing for our moment distribution. So we are going to match exactly what the computer is doing. It's not really an approximation as long as you do enough distributions. Now I can do the column the same exact way. What the code says is just assume the far end is fixed on a column. That actually, for the equivalent frame method, it says that. So there's no rigid zone here. So the only difference between what we just went through and the column is there's no far end rigid zone. So I'm not going to do that again, but just it's exactly the same as this without that rigid zone. So this continues, M over EI goes like that, continues. The only infinite zero curvature is at the bottom end of the column. So if you want to prove the column stiffness factor, that's how you do it. So I will again give these values to you. It's up to you whether or not you want to prove, I think I say prove one of the beams. If you're, like I said, you're really aggressive, you just love this stuff, can't get enough, do both the beams and a column. We don't care for the moment distribution what the carryover factor of the fixed end moment is. There's no load on the column, so we don't calculate that. But we do need to know what the stiffness factor is for the column. And it gets pretty far from 4EI over L. These columns are extremely stiff. They're not particularly tall in a parking structure, and they're pretty beefy. So this is what I do want you to do, and this will be mandatory. You need to calculate the distribution factors. And that's what I want. I want you to actually verify those with me too. You really shouldn't go on past this point. The PT data output that I give you is not going to tell you what the distribution factors are. So this is the one of the few things that you're not going to have in the computer output that I give you. So you kind of do need to come to me and make sure this is right. If these are not right, then pretty much every calculation you're going to do after this, I just realized that is misspelled. Wow. All the iterations of this book. Sorry. Okay, so I want you to take the beam moment of inertia. You will have calculated this, but you can verify this stuff. The top column stiffness. Remember, I'm giving this to you. So all my columns are 11'4", so they just have one. You may have two different column heights, so you pick the correct one for the top, one for the bottom, and figure out the stiffness factor first of the columns. So I've said the stiffness factor is 7.043 EI, I of the column, over L. So calculate that. The stiffness of the beam in span 1 4.343 I of the beam, the E's are going to drop out, they're constant, over the length of that beam. So figure out what that stiffness value is. Same thing with span 2. I've told you that the stiffness factor is 4.497. E's drop out. I of the beam over L of that particular beam gives you a stiffness there. So remember that we're now calculating the distribution factors, and it's kind of like what we did before, except we're going to have columns and beams framing into the joint. So the distribution factor standing at A, looking towards B, over here, is going to be the sum of all the elements framing into that joint. So the elements framing into that joint are the beam on this side. Actually, I should go back to the correct picture. Distribution factor AB. We're standing at A. We're looking at B. What's framing into this joint are two columns and a beam. So we're looking at the stiffness of that beam, the stiffness of this column, and the stiffness of that column. So the stiffness of the beam we established at 667.6. There are two columns with a stiffness value of 1432.2. This is the stiffness of the beam. We're looking at the beam distribution factor. The sum of all the elements framing in are two columns and one beam. So the percentage that's going to go to the beam is 18.9%. So that's the distribution factor for the beam standing at A, looking at B. Distribution factor standing at B, looking back at A, is the stiffness of that beam divided by the sum of the stiffnesses framing into that joint. There are now two beams framing in to the middle joint. Two columns framing into the middle joint. The beam to the left of the joint has this stiffness factor, so the stiffness value. So the distribution factor from B to A on this side of the joint, standing at B, looking at A, is 0.148. And you do the same thing here, and you do the same thing here. So these will be this is how you calculate your distribution factors. Okay? Remember, you have carryover factors that are not 0.5. This is how our moment distribution is going to be set up. So I proved this one to you, the 0.524. That's the carryover factor. So for any moment here, the way it gets affected over here is 0.524 of that. Not 0.5 like we've been doing all course up until now. And you got 0.533 on this side. So again, we're matching the computer, and you'll see that it's going to work. The fixed end moments for the span 1 beam is WL squared over 11.63. So if I'm looking, right now I just want to do the dead load, moment, and shear calculations. Dead load, moment distribution first. Total dead load is 1.645 kips per foot. WL squared over 11.63 is a fixed end moment of 543.7. The fixed end moment in the shorter bay is 277.2. So that sets up our moment distribution. Remember, we're using the right-hand rule. That's the fixed end moment on the left side. That's the fixed end moment on the right side. The signs come from the right-hand rule. Do the same over here. That was the fixed end moment. Positive this side. Negative this side. Got our carryover factors, got our distribution factors. We're all set to go. Now, be careful about how you do this. You're not seeing all the numbers, so you can't do what you may have done previously and go back and add up all the numbers to see where you are, because most of this moment is getting distributed to the columns, and you're not seeing those numbers. I mean, if you want to write those out, you can write the portion that goes to the upper column, you can write the portion that goes to the lower column. It becomes a bookkeeping mess, but you can do it. So what's happening here is you see a major drop-off. You started with 543.7. You've distributed negative 543.7 in that joint, but a whole bunch of that went to the top column, a whole bunch of that went to the bottom column, and the portion that just goes to the beam is 18.9%. So 543.7 times 0.189, negative is negative 102.8. That gets carried over, but by 0.524 to this value. Same thing here. We started with negative 277.2. We've got to put the joint in equilibrium, so we need to add 277.2 to the joint. A whole bunch of that 277.2 goes to the top column, a whole bunch goes to the bottom column. Only 25.4% of that goes to the beam, and that's how we calculate 70.4. 277.2, hopefully, times 0.254 is 70.4. That carryover goes here, 0.533. Not 0.5, but 0.533. So we continue, we add up what we have here, change the sign, and again, distribute 0.148 here, 0.216 of that here. That gets distributed, 0.524 of that goes this way, 0.533 of that goes this way, and then we go through that process again. Remember, don't run back up and add up everything before, because you're missing all the numbers that went to the columns. So you're not going to be in equilibrium just with these numbers. But the portion that got carried over, remember, it was in equilibrium prior to the last distribution. So when you send a number over, it's only out of whack by that much. So you're only putting a negative 32.6 back in. You really don't have to consider what happened before, where those numbers went. Because it was in equilibrium here, it's in equilibrium here, it's in equilibrium here. So you're only putting it out of equilibrium by the amount that you carry over. So that's the only number you're really worried about. These are actually simpler moment distributions than what you had been doing, because they converge so fast, because so much of the moment is going to the columns. So we distributed this out. We looked at 0.254, negative 32.6, calculated negative 8.3, carried that over, 0.533. So you see the process. It's similar to what you did before, but converging much faster. You'll get these numbers. These are the center line moments for dead load. So now we're going to calculate the shears. And the interesting thing here is, you've got to go through this. You need the shears, but the shears are now going to help you figure out what the moment is at the face of column. And that's actually the trick here. PT data is not going to tell you what the center line moment is. You're actually not going to be able to look at that number and see if you did it right. You can send it to me, and I'll check it. I will check your moment distributions and see if you're right. I'm happy to do that. You will know if you were right, basically, by calculating, setting up the loading diagram, calculating the shears on the left and the shear on the right, creating the shear diagram, and then reducing the shear diagram to the face of the column. Once you have done that, you can calculate the area between the center line and the face of the column. You subtract that area from that moment to get that moment. And that's actually what I'm doing right here. The moment at the face is the center line moment, that 459.1, minus, this is 1 foot, $49.4 plus 47.8 divided by 2. That tells me what the moment is at the face of the column. That's actually the moment that you can check against PT data. That's where we're going to check stresses. That's where stresses are checked. We're not calculating stresses at the center line of an infinitely rigid joint. We're calculating the stress at the face of the column. We're going to design the flexural strength not in the middle of an infinitely rigid zone, but we're going to calculate the strength that we need, the rebar that we need, based on the moment at the face of the column. So all of these face of column values are the important ones. Those are the ones that you will check in PT data. And lo and behold, I've done that. I should have the positive moments and the negative moments. And you will be surprisingly close. And I mean within a decimal point, typically. If you just keep the significant digits going and you do, moment distribution that really gets you to 0, you're doing exactly what the computer's doing. So there's really no reason for you to have a different answer than what the computer's getting. I mean, if you're off, and I'm not saying you have to, but if you're off by more than, 1% or so, 2%, you might want to re-look at what you've done, because at that point you almost probably have a mistake. And I know I sound like I'm being harsh, but it's just the truth. It's just you will be very accurate with these. You're not going to be as accurate in the positive moment region because PT data is discretizing the points that I've told it to do. I've told it to break this span up into so many, 12 or whatever I've done locations. This is always the face of column number. The first one in is always the face of column. The next number is always h over 2. It knows that PT data knows you need that h over 2 when we get to the shear. So the next one is h over 2 from the face. So those two will always be the case. And then I'm able to tell it how many more values I want in between. That's in the configuration. So you don't have to worry about that, but I'm just letting you know. But so in your positive moments, you may not be quite as accurate as nail it just as much as you are at the negative moments. The negative moments are all being done at exactly the same location that PT data is doing it. You and PT data are in sync there. This is actually calculating, the maximum moment may be right at midpoint, may not be. You have to look at which one of these is going to be the maximum. In this particular case, it is from the discretized points right at 31 feet of the 62-foot beam, but not necessarily the case. But this is what you will check. You don't need me at this point. You're checking the moments at the face and in the span. These are your dead load moments. I've given this output. If you've got PT data, then you can run this and check it yourself. And you'll know if you're moving along just fine. Like I said, don't be shocked when you're less than 1% difference, because there's no real reason not to be. So your live load shear, I made life easy for myself. I have constant dead load in both spans, which you're not going to have. Remember, I had 1.645 in each span. You're not going to have that because I'm not that nice of a guy. I don't want you to be able to just ratio these things. You're going to have to do a live load moment distribution. I'm sorry. You're not going to be able to do what I'm doing right here. I've never given the students constant dead load in both spans, the same dead load in both spans, and the same live load in both spans. If I did, you could do what I'm doing. You could just ratio. I don't do that. So I make it more fun for you. You're going to do 3 moment distributions: a dead load moment distribution, a live load moment distribution, and an equivalent load moment distribution. And I'm sorry. So I go through the whole thing again. I'm sorry. This is just a ratio of the dead load moment that I was able to do. You're not able to do that. You will come up with your own live load shear and moment based upon your new live load moment distribution. The equivalent load, we're going to do the same thing. We will calculate the equivalent loads, or we have calculated the equivalent loads. We will come up with fixed end moments due to that. By the way, your equivalent loads you can also check with PT data. That's in the output that I give you. It's the balance load. So again, you calculate that, you check it with PT data. You don't need me. Only time you need me is if you can't match these values and you're ready to pull your hair out and you're getting frustrated. That's when you need me. So remember, equivalent loads are going up, so all these signs are different. The fixed end moment, right hand rule, these reverse. but everything's still the same. It's the same distribution factor, moment distribution, same carryover factor. Consider that the stiffness matrix. The stiffness matrix never changes in a beam or a building. It's just the loading that you put on it. So the loading that you put on it starts here. But the stiffness matrix, the stiffness assumptions, doesn't matter if it's the dead load, the live load, the equivalent load, or you felt like putting another load on. That's what you have. So I go through the same thing, calculate the equivalent load. I want you to draw it to the tension side. Reduce it to the face. Get the moments at the face. Check that. Also versus PT data. That's under balance loads. Equivalent loads, balance loads. Tomato, tomato. For both spans, check your own work. If you can't get it, come to me. Most of you do get it without coming to me. That's what I really like about this. Okay, so we've established the face of column moments, dead load, live load, equivalent load, and we've established, well, that's what we've established. Oh, and the shears. Okay, so we've got the shears, we've got the face, dead load, live load, equivalent moments. So now we're going to check stresses. So what I want you to do, and I think I'm going to have you do this at each location. It's not a lot of work, but just take your face of column, span 1, left column, your dead load, your live load, your equivalent load, and get a total moment there. It's like your homework assignment now. We can superimpose all these. In the span, take your positive moment dead load, your positive moment live load. This will actually create tension on top, your equivalent load, and come up with a total load at each location. So each face of column and both spans. Not particularly difficult for you to do. You have a direct compression, F over A, right there. You know the section modulus to the top and the bottom. Start checking stresses. So at span 1 on the left side, left column face, span 1, right here. Take that moment, multiply by 12, and divide by the section modulus to the top. We're calculating the stress at the top of the beam at the face of the column on the left side of span 1. Subtract F over A and come up with the stress there. At the bottom of that same location, you're just looking at the bottom of the beam now at the left side of span 1 at the column face. Same moment, multiply by 12. Now you're dividing by the section modulus to the bottom. Minus that same F over A. Tells you what the compressive force is in the beam at the bottom at that location. Now I want you to do, I think I'm going to have you to do span 1. So now you have tension at the bottom. So this will be a tension value. Keep track of where you have tension and where you have compression. But your net moment is creating tension at the bottom. Divide by the section modulus at the bottom, subtract F over A, and yes, you've proven you have tension at the bottom of that beam. Check at that location, span 1, maximum. By the way, just take your maximum moments. These may not be occurring at exactly the same location. Just take your maximum dead load that you calculated, your maximum live load, and your maximum equivalent load. The fact that they're not exactly at the same location, these are parabolic moment diagrams. They're very flat towards the span, in the middle of the span. So if you're off a foot to the left or a foot to the right, you're not changing your moment value very much. And that's why you will still find that you're surprisingly accurate when you just add all the maxima together. So that's what I want you to do. And calculate, like I said, the stresses top and bottom. Do that at all locations. And this is my summary of this. This is what we just calculated, 0.269 and 0.088. And I want you to check that against PT data. And again, you're going to find that you're surprisingly close. I mean, I'm not kidding that I nailed it to the third decimal point here. In the span, missed it by 1/1000th. Again, PT data is checking at one location. I'm adding up the sum of all of them. But I'm really close. I'm really close. 0.269, 0.268. Close enough for government work. This one actually tended to be exactly the same. 0.173. I calculated 0.174. 0.1268. I got. Okay, and you're going to also. And that's the stress check portion. We check against the allowable stresses. Your compression should always be fine. This is just an academic thing that we ever do. I mean, if you have a compression problem, you have real problems. You're checking against the maximum tensile stress, square root F prime C, in this case 5,000. We can go for the 7.5 square root of F prime C, we can go to 530 psi. We're less than that. All of our tensile stresses were less than that. We're okay. What does that mean? That means we have set the force and profile. This force and profile, we've just gone through a lot of work, gives us a service level stress situation at all locations, all maximum locations in the beam, that satisfy the code requirements for compressive and tensile stresses. So now we can't touch it. We cannot change the force. We cannot change the profile. We're locked in with those. So I want you to write that. This locks in the force and profile. So when we go to the flexural strength calculations, we know what the force and the tendons are. That's now a given. We know the location of the CGS at all locations. We have to. We've established and set that. So now when we do everything else, those are given values. Okay, we're going to stop right here for this lecture, and we'll pick up at this point on the next one. Thank you for listening.